So, Blame the Badge. We are here to tell you the story of how an Area 41 badge can be blamed for some things. Extensa is a really fun story. It's a bit more fun than my history. One caveat, we don't do this full time. We do this on our weekends, sometimes with a beer. We spend some hours every month on the topic where time allows.
Yeah, I also don't have much to say about me. We talk about Extensa today.
Okay, so this all started with a conference badge that some of you guys actually have around your necks, the older one. And we received the ESP 8266, and doing what we do best is we take the badge, we take it home, we forget about it for a while. But at some point, we try and break things if we have enough time. So the next generation follow-up of the 8266 chip that you find on the badge looked a bit interesting, and I put out some alerts to watch for the hardware availability of that specific chip and some dev boards. I basically wanted to build a small device where I can send a message home that said, hey, I'll be home in 30, or the girlfriend could do the same thing, and whoever's at home could prep the food. Simple e-ink display, didn't have much in terms of what was needed. Then shortly afterwards, a colleague of ours at the time went ahead and he built a POC device, basically with the 8266 as well, to ensure that the plants at the office won't die. And he took the device, it was also distributed at Swiss Cyberstorm at some point, and my ESP32s arrived at home, and again, too many devices, too little time, left it on my desk and kind of forgot about the whole thing.
Okay, so I was walking around in the office and I'm a thief. I stole his devices and wanted to play around with it, but I forget about them and they were idling on my desk. So while after this, I started playing around with Mongoose OS, which is basically a web server on the ESP, and tried to make it manually crash with burp, and found something interesting. You can crash the web server because it's not handling multipart data properly. So we can crash IoT devices. At the same time, a customer had an IoT project based on Mongoose OS, and he claimed there's nothing to exploit. We don't have an operating system on this thing. Turns out the customer was not aware that there's at least 2 operating systems running before his app is running on the device. So you can exploit it. And yeah, then we thought, okay, we can do something with this. Let's write the IoT botnet and a paper about it. It's a very time-consuming task, and we did not finish it so far. But we learned a lot about the architecture and went deeper in the rabbit hole.
So this, we decided, because we're software people and we mostly do software testing, it would be funny to submit a workshop to hardware.io. In the Netherlands, so we showed people our findings or our misconceptions or a combination at the time, and how to get the general setup ready and how to get the configuration up and running. And after some feedback from the workshop, we decided to turn it into a talk. This took us to Bucharest in Romania, and over time the audience grew a bit, and the hardware.io organizers also do Nalcon in India and in some other locations. And they told us to modify the research a bit, compare it to ARM, make it applicable to what people already know, and present this. So this is where we learned that after-talk selfies is a big thing in India. And Antoine, if you're in the audience, please don't troll us afterwards. So today we bring you back to complete the Ouroboros of conference time by presenting our time-lagged findings about these specific devices.
Okay. So today we will take a look at Extensa especially, because for x86, ARM, MIPS, and Spark, exploitation has been done a lot in the past. It's very good documented, and techniques are well known in the public. This is not to say those are not interesting. They're actually pretty interesting. But new platforms arrive, and we will look at the extensor architecture. Compare the difference of the two most famous implementations or platforms, the ESP8266 and the ESP32, and we compare it a bit to ARM. We also take a look at the mitigations available on modern architectures, while on extensor, none of them are implemented. There's just architecture inherent non-executable stack for mitigation of stack overflows. While we compare these architectures, especially the both ESP8266 and the ESP32, we will see that there's a very interesting thing about the ESP32. It has a thing called register windowing, and we will take a look at this to understand it better in the view of an exploiter. And we are closing with instructions on how to set up your own lab and how to perform efficient debugging. And we conclude with showing you a proof of concept exploit, a buffer overflowing on extensor with redirection flow using ROP chains on the ESP32.
So, I always like to show these slides. Security and privacy are silent prerequisites. However, not too many stakeholders will talk about them. Everybody takes these things for granted. And the problem is, securing a solution, we know that it usually needs time. And this is typically a strong contradiction to the market requirements that are out there. Especially in environments where people go for a prototyping speed versus security, at least initially.
So this is the badge from the last Area 41, and yeah, we got this nice badge, and it was blinking around. You have some weird light show on it when you press different buttons. However, we were mostly impressed that the badge had Wi-Fi on the hardware. So we thought this is very special. I haven't seen something like this before. So I was excited, went home, and the badge was lying around on my bookshelf for 2 years. But later, with the stolen devices from Carel, I got back to extensor and started to take a look at the architecture specification and ended up reading the 700-page instruction set architecture reference several times and went looking into the code which is actually running on the device. Especially the difference between ESP8266 and the ESP32 were highly interesting. The extensor architecture allows the processor designer to design a processor to his wishes for specific use cases such as digital signal processing and IoT. And especially the IoT part is interesting because Espressif is marketing the ESP series explicitly as IoT platform. Those devices are highly connected, offering Bluetooth low energy and Wi-Fi connections. And further, Espressif is offering the ESP IoT development framework, which allows you basically to build IoT apps almost instantly without any knowledge about hardware. And to top that, if you use the Mongoose OS framework, you can even write hardware code in JavaScript. But why do we talk so much about the ESP32? It offers the register windowing. It's a technique which allows for much more higher code density, which is important on embedded devices as you don't want to waste cycles. And some of you might have seen this in the past. There's the Spark architecture, which also is offering register windowing, and the Intel i960 chipsets, which were mostly used for military use and slot machines. This is interesting. And finally, I had a use case for the stolen devices. And don't leave traces in your code. Okay. As mentioned before, we identified a denial of service vulnerability in the Mongoose web server. However, no code execution so far. Interestingly, the CTO of Sesanta wrote a blog article about stating that developers should not use the web server within the Mongoose OS framework, which is funny because Mongoose OS is named after the Mongoose web server. They should instead use client-side libraries like MQTT. The fun fact is, at this time in the GitHub repository of Sesanta and Mongoose OS, all the examples were using the web server for communication. So, not so fast. Our colleague Durbin, he has a talk about fuzzing tomorrow, identified a remote code execution vulnerability in the Mongoose OS MQTT stack with his fuzzer. So the client-side code seems also not to be the silver bullet for avoiding memory corruption.
So, besides the obvious differences of the ESP32 having Bluetooth Low Energy, what these devices have in common is that on both of them, the stack is not executable. And as you can see here, from the ISO definition, it doesn't look like there's much difference. Here we have 0 on the have windowed, and there we have a 1. How much difference can that cause on the actual architecture? Here we have 16 registers, there we have 64 registers. You know, how bad can it be to do exploitation on the one versus the other one? And yeah, Philipp will mention later how this made our life a little bit more interesting. Apart from the registers and things like register windowing, the ESP32 has a bit of a highest frequency and a dual-core CPU called the Alex 6.
Okay, so on this slide we can see how much the code of the ESP8266 called 0 ABI and the ESP32 register windowing differ. This is both extensor assembly, but the register windowing gives us a lot higher code density. As you can see on the prologue and epilogue of the function on the right side, there's only the entry call, and then you have the return window.end call, which is basically everything for prologue and epilogue. As on the other side, there's a lot of operations happening on the stack. And on the return, there's also a lot of actions happening, and the stack pointer is increased. This is a bit sad because we want such code on the ESP32 to have it easier to write exploits. But it's not so easy to find those good gadgets in the ESP32. As we need to increment the stack pointer and write to the instruction RAM. Okay, so when register windows are used, we basically refer to this as a stackless architecture. So what we know from normal exploitation, at least in some other environments, you want to be able to push and pop. So here we don't have any push and pop. But we need a gadget that needs to do the following. First, we need to populate the registers. Then we need to be able to write values to the instruction RAM. Finally, we need to adjust the stack, increment the pointer. And we can all do this if we basically try to find gadgets in the existing code. So now a bit more details on the register windowing, which is a crucial part for exploiting. The ESP32 has 64 registers, but you can only see 16 registers at the same time. So what's happening exactly? On each subroutine call, the registers are rotated. So if I call a subroutine, the subroutine can use all 16 registers, and the other registers are saved. This allows us to use a lot of registers and obviously don't do a lot of stack handling code, memory handling code, which is time consuming. So how's this functioning? Exception handlers are triggered on function calls, such as call x4 or call x8. And then the current active registers are moved to either free and invisible registers, or if all physical registers are exhausted, they are moved onto the stack, and this is what we actually want to happen. After 4 subroutine calls, all of the 64 registers are exhausted, and now the stack is used to store the registers, which we can overwrite. To visualize this, we made some nice graphs. On the left, you can see how the ESP8266 and ARM is doing this. Basically, the stack pointer or frame pointer is adjusted, and all the data is on the stack. On the right, you can see, I cannot see it on this graph, but it should show register windowing. I didn't draw it. It's Carel's work.
Yeah, blame the other guy that's offside. So on this screen, what you see is what we're aiming at memory corruption. And what happens in technology, technically, it's always a race. So you have attack vectors being found, you have the attack vectors being exploited, and the technology mitigation techniques need to be put in place in order for the vector to not be exploitable anymore. So many of these mitigations were put in place on modern processors or on software. So stack canaries, address space layout randomization, non-executable data memory, all of this was implemented on software initially, with CPU manufacturers then catching on and implementing the NX on the architecture level. And with IoT devices and their low power requirements, these mitigating features might not have been important initial features that were implemented for platform providers and hardware manufacturers. A crucial point that we need to get here is that all of these canaries and ASLR techniques, register windows, are just ways to cope with the aftermath of a particular overflow. And the data was still damaged. The attackers accomplished the 2 things that they wanted to do. So access data, change execution flow. Ideally, we want to prevent this earlier, and we want to prevent the overflow from happening at all. So we can do this with rigorous compile time analysis, or at least by blocking the overflow attempt at runtime, turning this into an exception. So the application would still stop functioning properly, but at least it does this cleanly and in a way that doesn't make the attacker's other computer, or your computer, their other computer. And it doesn't do this with blindly keeping on going with damaged memory structures. So all of these things can be done and can be implemented to avoid memory corruption, depending on the system. It's still me, sorry. To show you a visual example of code density, and we said that code density was important for a couple of reasons. Code density is important because we want, in low power devices, we want to basically not drain the battery. We want to put that device into low power mode and have it function for months with an e-ink display and a little battery. So we have a hello world piece of code there. Then we compile this for ARM. This turns out to be 9 instructions in total. And then we do this same for Extensa, and that ends up being only 6 instructions. So we have less compiled code that's actually being generated. And on this screen, you can see the mappings. If you're familiar with ARM exploitation, if you've done some router hacking in the past, you can see that it's a similar architecture, general purpose registers. We have a stack pointer, a return address. It's basically all the same. Most of the ARM exploitation knowledge is transferable to the Extensa platform as well. And here you have your mappings to save you 5 minutes of Googling. The A0 return address, R14 on ARM. We have the general purpose registers there, and the general purpose registers on the ARM, and the program counter being PC and R15 PC over there.
Okay, so let's have a look at the instructions available on both of these architectures. And yeah, you can on ARM, a simple ROP chain would be a gadget like using a gadget like POP R1 R2 PC. But as you can see, Somehow I didn't also include those instructions for the ARM, but there's no push and pop instructions on Extensor. This means that our ROP gadget needs to adjust the instruction stack with the help of the gadget. And this means increasing the stack pointer manually and setting a new return value, as we cannot simply pop from the stack, which will move automatically the stack pointer. And now we come a bit to the debugging part. Debugging hardware sucks. Working with hardware is time consuming. You have to do a lot of rebooting, reattach the debugger, and you need to flash it a lot because you want to try different code, and you need to think of like flashing the device several times a minute. And on the ESP, I don't know if someone of you already used the ESP series. If you try to flash more than once in a minute, you need to remove power from the device, let it relax a bit, and then you can reattach the power, and then you can flash again. And it takes like 10 tries for one device. So it's very time consuming. Also, OpenOCD is sometimes a bit buggy. I've seen several people struggling setting it up correctly. And the most bad part about this is you can only set 2 breakpoints on actual hardware, which is extremely limiting if you have a dual-core CPU and want to debug just one procedure. Also, I cannot solder that good, and the cables always go wild. What I actually want is this, which you cannot really see that good. I hope in the demo it's better. So we have here on the left, with the laser pointer, you see it better. I have started QEMU ESP. On the right, I have attached the debugger, and here I have the code with, I can automatically flash it into the ROM because I'm emulating this. And now I tell you how to set up a setup like this to start exploring the architecture. So the first thing you do is you can set up QEMU. And QEMU has Extensor support for a very long time now, and it's quite stable. But we focus on the ESP series, and we want to use the ESP IDF, especially for using FreeRTOS on the device. So we need QEMU ESP32. If you set up QEMU ESP32, which is a bit painful because the documentation is updated in a long text, and he's not removing the old parts. You will actually need the hardware, or at least a boot ROM file, because this is not shipped with the QEMU. You can find this in some GitHub repositories, and you can also drop us a mail for this, or you can even use your actual current badges to dump the ESP8266 boot ROM. Next, you will need to set up the ESP IoT development framework, which has all the tools you need, like compilers and also tools for analyzing your code, especially the boot ROM, which you can do with object dump. It's quite a good tool because the Extensor toolchain or the ESP toolchain removes the ELF headers of the binaries before it flashes them to the device. So most of the normal ELF analyzing tools will fail to analyze this properly, especially resolving symbols. And object dump can do this. So then you need to set up a good tool for this assembling and analyzing binaries. We prefer Rudder 2 because it's very good, and it has very, very good support for Extensor. And also it will not make you poor.
Yeah. So after this, it's time for GDB. We use the GDB provided by the QEMU ESP32. But it's also possible to use other debuggers via the GDB server. And to have a better overview, we strongly suggest you use GDB dashboard, which Philipp already showed you. Hopefully it's better in the video, or we have a bit more contrast. As this makes the registers and everything, puts it in a nice viewable dashboard that we have available. At the time, GDB PETA didn't work that well for us. After that, the next step is to get everything to display in one place. So once you've run through all of the pain points of flashing, reconnecting the device and all of that, when we run it in emulated environments, we want everything on one screen and easily accessible. So for this we use tmux. You'll need at least 3 windows to efficiently debug everything, depending on your preference there. And if everything is already set up, you can write your vulnerable code to explore the actual architecture. And then the final step, start exploiting your code, investigate the crashes, try to learn where the data actually goes on the stack, what registers are being affected. You need to be able to find gadgets, which we'll go into a bit more. You need to build ROP chains, and finally, hopefully, you can profit. So in previous talks, we've shown a POC of ROP chains working on Extensa, but today we'll show you a ROP chain working with actual gadgets that exist or pre-exist in the ESP IDF created boot ROMs. First, perhaps we need to go into what are gadgets and what are they good for. So essentially a gadget is a piece of pre-compiled code that exists in a boot ROM or deployed on the device. It pre-exists in the system that you want to exploit. And this is the difference between a perfect gadget and a fake gadget. Sometimes for demos, people do a fake gadget, which is just code that you create, that you can then access and reuse over time, but it doesn't necessarily exist in the boot ROM. So for a perfect gadget, we want something in the boot ROM that exists, that is a small instruction set, like 5 or 6 instructions. It accomplishes something by allowing us writing to registers and allowing us to affect the information flow and execution. A fake gadget is something that you put in your code and that you deploy. It's useful for a proof of concept, but it's not useful because you can't exploit existing systems that are out there in the wild. So for this very ugly slide, what we have is we have some perfect gadgets for the 8266. We use this pre-existing code to populate registers. If we need to write data, we use this function with ret_n. You'll see the difference on the next slide. And then finally, we use isync to inform the CPU that we've updated our instruction set. So this would pre-exist in the boot ROM, and it's code that we want to basically point to execute, but with different data for us.
So, but this code is only on the ESP8266 boot ROM, and you cannot find code like this in the ESP32 boot ROM. On Sunday, I was reading a lot of disassembled code. So it was this Sunday. I was very sleepy, but highly caffeinated. And I discovered these gadgets. I was some kind of in the zone, so I don't know how. So first of all, these gadgets are a little more complex than the gadgets we had on the previous slide. These consist usually on, at least the first 2, on a lot more instructions. And let's talk about the gadgets. The first one, we actually only use this to increase the stack pointer. Where's the pointer thingy? So this call here is increasing our stack pointer. This is not so important, it will be trashed. That's the return value for the gadget, so this must be the address of this one. And so this is just to increase the stack pointer and jump to the next gadget, which is a bit more interesting. This is the populate register gadget, and this is a quite big gadget. And also, slight side note, this gadget is calling another function, which is calling trashing some registers we've populated. Anyway, so the populate registers gadget has about 27 instructions. This is why you cannot find this with tools. You need to read the code, because most ROP gadget finding tools search for gadgets in the size of 5 to 7 instructions. A good thing about this gadget is it's populating all registers. So this allows us to choose for different write gadgets, because we have data in all registers. We chose this write gadget. This is storing the data stored in the register A14 to the address stored in A15 plus the offset 60. Then it is loading a new return address, which is the isync gadget, and yeah, it will sync the instruction RAM. And one noteworthy thing here is you can only write to instruction RAM using the operations S8Y, I, S16I, and S32I. All other operations will trigger an exception. So, demo time. Maybe we can turn the lights off here. You need to point to this. Where's my cursor? Okay. Yeah, I think you still can not read it that good. Okay, so this is the debug environment. We have the QEMU call up here. And we already have attached, I know it's really bad to read, but we will upload it in a better resolution later. So, and I set a breakpoint to the first gadget, which is triggered after the initial overflow. So now it is triggered, and we can see the instructions of the gadget here. We can see that the stack pointer is increased. Now we step through the code. And this is a function call. It's a lot of operations happening, which you usually don't want a ROP gadget to do. But it's just trashing 2 registers, so we can live with that. So now we are populating all the registers. You can see we populate registers starting from A3 to A15. And then we jump to the write gadget. And now we take a look at the memory, instruction RAM. And you can see we wrote area into the instruction RAM. So this is actual gadgets existing in every ESP32. And yeah, I didn't have enough time to do more of this. What we do in the next steps would be to do actual shellcode and write implants which change the behavior of the device without deleting its original function. So, and next slide, you already saw it.
So, what are good reasons for blaming the badge? Step 1, we can blame the badge for being very frustrated for a very long time. Trying to get things to work with register windowing, crashing our registers that we've overwritten into all the time. It took some time to inspect how the architecture worked. Step 2, you need to go and present your findings. So present your frustration, ask people for examples. At hardware.io, people gave us a lot of good suggestions of what we could possibly have a look at. Step 3 is to do bad post-conference karaokes, which led to that photo over there. And step 4 is profit. I mean, we have the real gadgets in the ESP IDF now, and it would be interesting to get persistence on vtasks on these devices and have them stay operational while having a backdoor into those devices. So if any of you guys want to join us for the actual paper or helping us expand the labs, please get in touch. And then I would just like to thank my employer for giving me the time to be here on a Friday and present this talk.
Yeah, me too. Yes, I thank for some time I could spend on research, and yeah, that's about it. Contact me via my new emoji domain email or on Twitter. Any questions?
Thank you for your talk. Are there any questions?
Don't be shy.
Nobody? Okay, so thank the speaker again.
Thanks.